All right, now in problem number 20, we're told that the probability that a fisherman catches a tuna in any one excursion, let's write that down. How about T for tuna? Is 0.15. So anytime this fisherman goes out, got a 15% chance of catching a tuna. And we want to know, what is the probability that he catches a tuna on each one of 3 excursions? Let's see how we can do that. First of all, he could get, let's get a notation here. He could get a tuna on, I'm going to subscript one to keep track of which excursion it is. So remember, a subscript now is just a name for this to keep track of which one it is. This is a tuna on the first outing, and he wants a tuna on the second outing, and a tuna on the third outing. Now, we're seeing these and, so we ask, are they independent? Problem doesn't say anything about it, but let's assume that they are. So we can multiply these together. So this will be the probability of getting a tuna the first outing times the probability of catching a tuna the second time out times the probability of a tuna on the third time out. And we're also told, well, we're told up here that the probability of getting a tuna is 0.15. So we're just going to multiply these together. So we'll have 0.15 times 0.15 times 0.15, and my calculator gives me this number here, 0.120, and I'm going to write a 3, and there's a 375, but I'm going to round this off to 34. Pretty typical to round probabilities off to 4 decimal places. Now, this problem also goes on to ask us, what is the probability, let's write this, so this is going to be the probability of getting a tuna on at least one excursion, at least one tuna. Okay, we want to get the probability of at least one. So the probability of getting at least one, how do you get one on 3 trials here? Well, we could get this. We could get 1 or 2 or 3. But now, here's this business of at least one again. So I think what we should do is, why don't we do this? Let's think opposite. And the opposite of getting at least one tuna would be, I'll do it up here at the top, the probability of getting none. Or let's say the probability of 0 tunas. Since we're thinking opposite, it's always going to be 1 minus 1 minus. But what we want here is this. What's the probability, 1 minus the probability of getting no tunas on the first, all right, so let's write no tunas on the first outing, and no tunas on the second outing, and no tunas on the third outing. Again, we're assuming that these are independent, so we're going to multiply 1 minus the probability no tunas on the first, probability no tunas on the second, probability no tunas on the third. So this is going to be 1 minus, now probability of getting a tuna is 0.15. Not getting a tuna then would be 1 minus that, 0.85, but we want 3 of those. And when I multiplied those out, I got this. I got 0.386. Now, in problem number 23, we're told that 30% of those over 50 in this Sleepy Valley place own CDs. So the probability of owning a CD, being that you're over 50, let's just say CD minus what it is, this is equal to 0.3, right, 30%. And what we want is this. What is the probability that among 4, so n is equal to 4, randomly chosen people, that none, what's the probability that none own a CD? So to get none, this must mean like some notation here, that the first person does not own a CD player, and the second person does not own a CD player, and the third person does not own a CD player, and the fourth person does not own a CD player. Nots. Okay, now these are independent, so we're going to multiply these together. Now, back up here, the probability of owning a CD player is 0.3, so the probability of not owning a CD player must be 0.70. So down here, we're going to multiply these. So we're going to have 0.70 to the fourth, and that comes out to 0.2401.